All right, today we're diving into something really cool. We're going to put one of the biggest ideas in all of physics, yeah, Einstein's theory of relativity, on trial. And get this, the star witness, the key piece of evidence, it's a clue that's been hiding in plain sight for almost 300 years. Look, Einstein's work is the absolute bedrock of how we see the universe. It's beautiful, it's powerful, and for sure it works. But what if that very beauty, that mathematical perfection, came with a catch? What if, by creating this perfect blueprint for reality, it kind of glossed over a messy but totally essential piece of the puzzle? So, to really get what this charge against Einstein is all about, we first have to step into the world he built. I want you to picture it like a perfect, totally self-contained box, a little universe where all the rules are pristine and internal. At the heart of this world is an idea called an inertial frame of reference. So just imagine you're on a super smooth train, moving at one constant speed. No bumps, no acceleration. If you drop a ball, guess what? It falls straight down, just like it would if you were standing still. Inside this moving box, if you don't peek out the window, you honestly have zero physical sensation that you're moving at all. Okay, so now let's run a classic little thought experiment right inside this box. We've got a special clock that works with a beam of light. We shoot a pulse of light from the floor, it bounces off a mirror up on the ceiling, and then it comes right back down. Simple, right? Well, how you see this simple event is where things get really interesting. So, from your perspective, sitting there on the train, that light just goes straight up and straight down. The physics is neat, it's tidy, it's totally self-consistent. This is what we mean by Einstein's blueprint view of the world. But what happens when someone outside the box is watching you fly by? Well, that's where our whole mystery really gets started. Every good detective story needs a mysterious clue, right? And for our case, we have to jump in our time machine and go way back to the 18th century, to a strange little anomaly that astronomers were noticing when they looked up at the stars. So in 1728, an astronomer named James Bradley was trying to look at a star he knew was directly overhead. But to actually see it, he had to tilt his telescope just a tiny bit forward. Now, why would he have to do that? Well, because the Earth isn't standing still, it's hurtling through space. By the time the starlight actually travels down the length of the telescope tube, the Earth and the telescope itself has moved. You have to lead the target, like a quarterback throwing a pass to a receiver on the run. This was the very first real proof that our box, our planet Earth, is moving through something. So, let's be really clear about the charge here. The argument is not that Einstein's math is wrong. No way. The idea is that his theory might be, well, incomplete. That by focusing so much on the elegant, perfect consistency inside the box, he might have left out the messy physical reality of the space outside of it. And this quote from the source material just hits the nail on the head. Einstein's theory is an amazing blueprint. It's an incredible set of rules for doing calculations within a certain frame of reference. But it might not be the whole story when it comes to physical reality itself. And this gets us to the real philosophical heart of the debate. Einstein's theory is all about internal consistency, making sure the math works perfectly within its own self-contained system. The challenge, on the other hand, is demanding external consistency, saying a model has to line up with physical, observable realities, like having to tilt a telescope to see a star. Okay, so this brings us to the challenger's alternative idea, and it's a cool one. It reimagines the universe not as a bunch of separate, independent boxes, but as one big, unified stage. And it's a model based on the real-world physics of trying to hit a moving target. Let's just break this down. First, picture the stage. Space isn't empty. Instead, it's filled with a physical medium, an electromagnetic field space, and that's what light travels through. Second, our train isn't just moving in the abstract, it's physically moving through this field. Third, because that train is moving, the mirror on the ceiling is a moving target. So step 4, to actually hit that moving mirror, you can't aim straight up. You have to aim it diagonally forward. This is what they call deviation shooting. It's basically field ballistics, where you always have to account for your motion through a medium. This model gives you this really cool picture of space having a nested structure, kind of like those Russian Matryoshka dolls. The biggest, outermost doll is the entire universe's electromagnetic field. And inside that, you have smaller dolls, like our galaxy, and inside that, our solar system, and then finally, our little train car. Each one is its own little partial space, moving around inside the bigger, absolute one. And this leads to another wild idea called temporal thickness. Think about this for a second. When you look around right now, you're not actually seeing a single instant in time. The light from your screen is reaching you almost instantly, but the light from the sun, that took 8 minutes to get here. The now that you see is really a collage, a mashup of different moments from the past, all arriving at your eyeball at the exact same time. Okay, so we have two competing models of reality, two completely different ways of looking at the universe. How in the world do you judge a debate like this? Well, the researchers behind this analysis did something pretty clever. They turned to a very modern jury, a whole panel of advanced AI models. The AIs were given 3 very clear choices. They could pick option A, the standard Einstein view, reality is the perfect blueprint inside the box. Or they could pick option B, the challenger's view, reality is deviation shooting through a universal field. Or they could go with option C, just stay neutral and say we need more data. And the results that came back were pretty shocking, actually. Claude AI came out swinging for option B. And its reasoning? It was all about physical realism. It pointed directly to our 300-year-old clue, the fact that you have to tilt a telescope, as powerful evidence for some kind of universal reference frame. ChatGPT was right there with it, also picking B. It said, this model just does a better job of explaining the stuff we actually observe. And this is key, it treats the act of seeing not as some abstract idea, but as a real physical process with real time delays. But hold on, not every AI jumped on board. Perplexity AI decided to choose C, taking the neutral path. It basically said, look, both of these are just interesting ways of reinterpreting the same data, and I'm not going to pick a side until there's more evidence. You know, a very cautious, very scientific approach. So here's the final scorecard. And wow, an overwhelming majority of the AIs actually sided with option B, the challenger. What's so wild is their reasoning. They almost all preferred what they called physical realism and observational evidence over pure mathematical beauty. Only Perplexity and Phalo DeepSeek held back, saying, hey, we need more proof. The AI jury has delivered its verdict, but this case is far from closed. In fact, it opens up a much, much deeper question. What do we want our science to be? Do we want a perfect, clean blueprint or a messy guide to the battlefield of reality? So even though the AIs leaned really heavily in one direction, the fact that we didn't get a unanimous decision tells you something important. This isn't about finding a single right answer. It's about a fundamental choice in how we see the world, what we value most in a scientific theory. And that's the big question I'll leave you with. What actually makes for a better description of our universe? Is it a pristine, mathematically perfect blueprint? Or is it a model that embraces the messy, complicated, observer-dependent reality of physical interactions? A world not of clean lines, but of field ballistics? The answer to that? Well, it might just shape the future of physics.